Hi everyone, I'm Kyungwoo. I'm software engineer working at here in Meta. I work with Manman and Ellis for this project. Today I'll be talking about our work on optimistic and scalable global function merging. The size of mobile apps keeps growing as we keep adding new features. The graph shows how quickly the app size has increased over the past year. Compared to the blue line on the top, take a look at the green line on the bottom. That shows it's growing relatively slowly. That's where size optimization come into play. Today, I'll be focusing on two main strategies for size optimization: function outlining and function merging. A function outliner finds repetitive code sequences and replaces them with function calls to a shared function. I focus on machine function outliner in this talk. We replace this, it replaces the same machine instruction sequences by native function calls, so the call overhead tends to be low. So you can effectively reduce code size. Here's the example with the two functions. The code sequence in green that are identical. If I outline them with a native function call, they will look like this, resulting in only 7 instructions on the right-hand side, as opposed to 8 instructions originally. Function merger works on entire function rather than specific code sequences, unlike the function outliner. A function merger also can handle similar functions by parameterizing differences. Function merger is implemented at the IL level, so the call overhead tends to be high because it needs to abide by calling convention. In this example, two functions, they look very similar to each other, except the call target constant, F1, F2. We may come up with a shared merge function with the additional parameter here, x2. The original two functions become the dunks while providing their individual context through this parameter. As you can imagine, for both function outliner or merger depends on entire intermediate representation called IR. They need to be explicitly compared in order to find same or similar instruction pattern across the entire app. This can be computationally intensive. However, our approach is based on using summaries that are applicable to separate or parallel compilations like thin LTO. So we have developed optimistic global function merging that utilizes these summaries to track the function similarities. Our technique optimistically create merging instances, and then they are folded by linkers identical code folding called ICF. In our comprehensive code generation framework, we've seamlessly integrated the global function merger and global function outliner into single framework. We also provide a single code generation framework that are applicable to distributed build environment. Our impacts on real-world mobile apps are substantial. I will get into detail in the later slides. Let's break down thin LTO with the global function outliner that has been published before. The key idea is to repeat code generations to get the sum global view. Basically, during the first code gen round, we performed outliner locally to find some local outline instances and then publish such opportunity into sort of global summary named global prefix tree. During the second code gen round, we identify cross-merge candidate, and then we create those instances. And finally, link time, if these two outline instances are truly identical, we can fold them through linkers ICF. Let me give you a more concrete example. Let's say we have two functions in the module 1, another function in module 2. They look very similar. The code sequence in green are identical, we can replace them by some function, outline function like this. However, the function in module 2, they cannot be outlined because it's singleton. There is no match within it. Once we have outline function, we compute the stable hash sequences that corresponding to machine instruction in outline function. Then we can publish into global prefix tree. This is merely compact representation of tracking hash sequences using traditional triad structure so that we can share the common prefix to save size in summaries. During the second cogen, with the same input, we can apply local outline same as first step. But now, because now we have a global prefix tree, we are now able to outline another instance in module 2. Please note that the outline function has unique name for safety because there may be chance of hash collisions. At the end, during the link time, if these two outline functions turn out to be identical, we are able to follow them safely. So now let's explore how global function merger is integrated into this system. Function merger was implemented at IL level. We need to push it down to pre-cogeneration hook first. Likewise, we need to repeat cogenerations. During the first cogen, we analyze the functions to create some stable function summary and then combine it into global summary. During the second cogen, likewise, we create merging instances optimistically and so on. Let me give you a more concrete example. Similarly, they look very similar, except core target constants are different. At this step, we just compute summary, which are independent of intermediate representation, as you see. It consists of function hash, which is based on contents of functions, except the core and the constant targets. So as you see, the hash are all identical. We have a different naming string. We keep track of constant location that is represented by a pair of instruction operand, instruction index, or operand index, etc. We can publish it into some global merging information where stable function summary are grouped by same stable hash functions. And then we can compute the parameters. That is the minimal set of constant location that vary across different stable functions. Now let's apply the second step with the same input. Now we are able to compare IR against the global summary that we just previously computed. As you see, now we create merging instances in module 1 and module 2 independently. Likewise, global outliner case, we create merging functions uniquely with unique name for safety. At link time, if they turn out to be same, we can merge them like this. So let me share some data on the size saving achieved by applying both function merger and function outliner. This graph compares several function merging techniques alongside with the global function outliner. The global function outliner alone contribute co-size reduction of 70%, which is significant. In contrast, the built-in default function merger or the LFM, which is local function merger, adapted from Swift function merger, result in only marginal size impact. However, our global function merger significantly improves the F size, around 3.5% in addition. I mentioned that earlier, our approach is based on repeating cogenerations. Repeating cogeneration, of course, increases build time, which is not good. More importantly, it may not be suitable for distributed build environment because we have additional synchronization point between two cogenerations. So we split them into two distinct pipelines. One is writer on the left-hand side, the other is reader on the right-hand side. Basically, former produces Gaussian artifacts that represent outlining or merging opportunity, while the latter, the reader, simply reads the artifacts and applies optimization in separate. We can also apply this framework into continuous integration environment, where target source code also can evolve. Basically, we can produce Gaussian artifacts infrequently on the left-hand side. The actual optimization builder on the right-hand side can consume these artifacts and apply optimization safely. As you can imagine, there may be mismatch between the writer and the reader. So we may have a stale summary that can negatively impact the app size. So we tracked the app size regressions over the last 3 weeks, refreshing Gaussian artifacts weekly. Take a look at the red line on the bottom, which is the case with outline only, which works pretty well, good well. The size of head is less than 0.2%, even though we have hundreds or 1,000 commits in daily commits in our repo. But if you look at the blue line, when we combine merger and the outliner, it can spike up to 0.7%, right before the Gaussian artifact update on the pop line. This graph shows comparison of build end-to-end build time that includes compilation and linking and everything else. The single Gaussian pipeline is about 9% faster than double Gaussian approach. In fact, if we compare just link time only, the difference is even larger. It's like about 70%. Depending on machine configuration and build environment, the size and the gap will be even larger. As you can see, adding the global function merger on top of the global function outliner, the build time impact is very negligible, no matter whether you use a single Gaussian or double Gaussian approach. So to conclude, I've demonstrated the effectiveness of our global merge function and also global function outliner that can significantly save app size by up to 20% when combined. I've also shown that our cross-module transformations can be applicable to separate compilation environment. Last but not least, finally we've gotten legal approval. So we have begun upstreaming all this code, starting with the global function outliner. This includes code generation framework that I just described, and the tools that can deal with the stable summaries offline. Please check out this link for our RFC and the PRs in LLVM, and follow our contributions. Thank you for your attention. I'm ready to take any questions you might have.
Hello. I have a question. So how does this play well? Like, how does this play with the inliner? Because you're adding with the inliner.
I didn't hear that very well.
With the inliner pass, does it work well with that?
I didn't hear the last Q.
Last question is, because you're doing function outlining,
yeah.
How does it work with the function inlining?
Function inlining typically happens only in the compiler pipeline. As I explained, the function outliner or function merge happens very late pass. So it's kind of sort of orthogonal, although it could be related. But normally the compilation flag that we apply for our mobile apps are under minimum size optimization, say OZ. I don't know whether you're familiar with that.
Yeah.
In that case, inlining is mostly prohibited.
Okay, thank you.
Thank you for the nice talk. So techniques are for reducing the size of code, right?
Yes.
But I wonder how it affects the branch prediction performance.
Oh, yes. Yeah, so basically your question is about the impact on the performance, right? So as you can imagine, it increases more function calls. So it may impact the performance in CPU or cache performance for sure. We actually have there's two things can explain. Mobile apps are not really bound to CPU. So size is actually more important than anything else. Because the smaller means actually the faster to start up, because startup performance is bounded by the memory page fault rather than cache performance. And also, so of course there's a case where we do care about performance, like scroll performance or sending message in the Messenger app, then we do care about performance. In that case, we have a PGO. So I didn't cover that in this talk. So we have a proprietary PGO technology. We also actually upstream the lightweight instrumentation that is compatible IR PGO in LLVM. We actually upstream that. So I'm happy to talk about offline. So if you're interested, yes.
Okay, thanks.
Okay,